Now, class, we want to talk about substitution reaction. So basically, the word substitution is not something that is new to us. It's basically a case where an atom replaces another atom in the course of a chemical reaction. If I have something like AX plus Y, and of course, there is a substitution reaction, this Y is going to replace the X. So this becomes AY plus X. Now, you need to understand something, that substitution reaction can be nucleophilic, can also be electrophilic. Now, depending on what is substituting. Now, this guy, if you look at this reaction, this is what is entering here, and this is what is coming out. This X that is coming out is called the leaving group. Like, this is what is coming out for something else to enter. Now, what is replacing this leaving group determines whether the substitution is going to be electrophilic or nucleophilic. If what is substituting this X, which is this Y, if this X is actually having a negative charge, the reaction is going to be substitution nucleophilic. If this Y is having a positive charge, it's going to be what? Substitution what? Electrophilic. So basically, the nucleophilic substitution or electrophilic substitution is dependent on what is replacing the leaving group. You understand? Now, another part I would like to mention is that if this Y, for instance, is having a negative charge, nucleophile simply means something that is rich in electrons. It can have a negative charge or a lone pair. If this Y,
if the Y is positive, right, that substitution reaction will be electrophilic, right? So whether a substitution is electrophilic or nucleophilic depends on the incoming substance that will replace the leaving group. Okay, so if the Y has a lone pair of electrons or a negative charge, that's a nucleophilic. If the Y has a positive charge, that is electrophilic substitution reaction.
Okay, so we have that of the nucleophilic and electrophilic. All right, so we want to focus majorly on that of substitution nucleophilic. All right, so that is what we're about to do now.
all right, so let's start. So this nucleophile replaces this X. Now, pay attention closely. This nucleophile is having minus. It enters here. The X is coming out also as what? Minus. This guy cannot come in as minus, and this guy comes out as plus or neutral. It's just replacing this X here. So whatever this guy is, the X is going to come out as that. So we say this guy is the substrate. Now, most of the substrate that is used for substitution is always alkyl halide. But in rare cases, you can also have alcohols. Now, why don't we normally use this guy? Because OH is a poor leaving group, right? Now, when we get to leaving group, we're going to talk about it. Now, we said X here is a leaving group because this is what is going to go out for this guy to come in. Is it not so? So anything that is going out, we call it a leaving group, right? Now, having said this, let's now talk about the mechanism of substitution nucleophilic. Once you just see SN, it is substitution nucleophilic. Now, we have two mechanisms here. We have substitution nucleophilic unimolecular. That's SN1. We have number 2, substitution nucleophilic bimolecular. So these are the two substitution mechanisms we have. Why do we call it unimolecular and why do we call it bimolecular? We're going to be seeing that shortly. So first, you need to know what substitution is. Like in Chem 365, what we're interested in is the mechanism. In year 1, year 2, all we just care for is the product, what is reacting and what is giving us the product. But here, we are more interested in how are those products formed. What are the steps that we're going to pass through? What are the intermediates? And all of those stuff is what we're going to be discussing here. Okay, so we'll take them one after the other. Now, you might want to ask, why do we call this guy unimolecular? It basically means that in the rate determining step, it only involves one molecule, right? in the rate determining step. Now let me tell you guys, let me give you guys an example. If you're climbing a hill, right, there are two processes. The first is a process of climbing. Of course, you get to the apex point. The second one is coming down, right? Which of these two determines how fast you're going to get to? Is it when you're climbing or when you're coming down? When you're climbing, of course, the rate determining step is when you're climbing. That is the step that requires the highest energy. Once you've gotten to the top, you can even leave yourself and then now there's what we call characteristics and there's what we call evidence, right? Now these are the things that what we're about to talk about now is actually what is going to make this course very interesting. What do I mean? In exams, they might just give you a reaction and they say, give the mechanism of this reaction. They will not tell you whether it is SN1. They will not tell you whether it's SN2, right? Now, it is left for you to actually look at the conditions given to you in that question, starting with the substrate, right? Now, from the substrate, you look at the solvent, right? From those two stuff now, you can equally tell, could this guy be SN1 or could this guy be what? So, that is why I want to talk about characteristics of SN1. Characteristics of SN1 reaction. Now, the first thing we have here, we have the reaction and mechanism. The next one, so the third one we have stereochemistry. If you actually can tell the difference between all of this for SN1, you're good for exams. What do I mean? The reaction and mechanism, this guy is a two-step mechanism, right? The first step is formation of a carbocation. The second step is attack by the nucleophile. The kinetics of this guy is always a first-order kinetics because just like I told us earlier, it's only one molecule that is involved in the rate determining step. So anytime we talk about kinetics, is how fast the reaction proceeds. Now, stereochemistry, this guy proceeds via inversion and retention. We'll talk about this. Substrate, this guy is best for tertiary alkyl substrates. Tertiary alkyl substrate, leaving group and solvent. We have polar protic, we have polar aprotic. So basically what we are trying to do here is that we are going to explain each of these for SN1, right? So you're going to see difference for SN1 in all of this, for that of what? SN2. So for example, now, well, let's not stress ourselves. So I'll clean this off. So we start taking it one after the other.
All right, SN1 reaction is a two-step process, okay? Now, as you can see on the board, I listed out the two steps. Now, the first step is the formation of a carbocation. All right, this formation of a carbocation is the most energy demanding step. That is, it is a rate determining step. Right, it determines, the first step determines how fast the reaction is going to proceed. Right, now the second step would now be attacked by the nucleophile on the carbocation. Recall that from the first step, we're going to form a carbocation. Right, carbocation is carbon bearing positive charge. So after the carbocation has been formed, the nucleophile will now attack the carbocation to actually form a substituted compound.
So let's look at this. Now, this is actually how questions most likely will look like. They'll give you a complete reaction. I'm supposed to give us a solvent here. Solvent. Let me not go and use wrong solvent. I'll check it out. Now, imagine you have something like this, and they say, give the mechanism of this reaction. Bear this at the back of your mind that they will not always tell you whether it is SN1 or what. Because if they tell you it's SN1, you already know the mechanism, right? It is left for you to look at this reaction and figure it out. Now, I have not gotten to substrates, but this substrate we have here is substrate for SN1. Because this is tertiary alkyl halide. Tertiary alkyl halide is best for what? SN1, because of the formation of a carbocation. So here, why do we call it tertiary? Because this carbon bearing this halogen is attached to three other carbons, right? So the first step Don't forget, it is the formation of a what? Carbocation. Now, what is responsible for that formation of the carbocation? You're going to hit this guy. Of all these four bonds, 1, 2, 3, 4, this is the weakest of all the bonds because this bond is partly polarized. Bromine is more electronegative than carbon, so it has taken some of the electron to itself. So any small thing you do to this compound, this bond will break. So the first step is formation of the carbocation. So I come here, I'll say CH3 now what will bring about this breaking is heat. When you heat this compound, this becomes CH3. This bond is breaking, and this bromine is taking the two electrons that belong to both of them. We have this. Now the second step will now be attack of the nucleophile on the carbocation. Now, this is a base. This nucleophile you have here, it is the OH that is the nucleophile, not the Na. So when you break this guy, now come here and say CH3, CH3. You can decide to do this. Or you can decide to do this because this is an ionic compound. This guy is going to break as plus and minus. Or you can just decide to remove the Na. It is the minus that will come to this guy. And once that happens, we have CH3. Now this Br, that is minus, will now combine this with this guy to form what? NaBr. So this is the mechanism of this reaction. First was to break the carbon-halogen bond, form the carbocation. The second guy was the attack by the nucleophile on the carbocation. Now, most times they used to use line structures or line formulas for this substrate. See something like this. Well, all of this is what we are going to be looking at shortly. All right, so let's look at the next guy. Do you have that past question here with you, Ba? Okay, but it has that one inside. Kinetics. Please put down. SN1 reaction. SN1 is a first order kinetics. It is a first order kinetics. And the rate law for SN1, the rate law equation for SN1 is rate is equals to K, where Rx is a substrate. Now this corresponds to what I told us earlier. And what did I tell us earlier? That SN1 reaction is actually the rate determining step is always the first step. And the first step is involving only the substrates. If you could recall, when you asked me a question, you said, why do I call it unimolecular? Because in the rate determining step, it only involves how many molecules? One molecule. And that one molecule is the what? Substrate. All right. So how fast this substrate is being broken down, right, determines how fast the entire reaction process would be. So this is actually the kinetics. So in case you are being asked in exams, how will questions come? Now let me tell us. They give you an equation. They said the following reaction followed a first order kinetics. Follow the what? A first order kinetics. Give the mechanism of such reaction. Now this, they've given you a clue to know what you're going to do, right? But some person will still be like, how will I know it's SN1 or SN2? The moment they said it follows a first order kinetic. First order kinetic is only for what? SN1. If they had said second order kinetics, it would have been for what? So that's just the concept. So that's that for kinetics. Or another way they can ask you question and involve kinetics is that they'll give you a reaction. Maybe they'll actually indicate something else that will make it to know it's SN1. Either through the substrate or through the solvent. Is it not so? And they now say I give the mechanism of the reaction. I give the kinetics. Give the what? Let's assume, for example, the reaction was Rx plus Nu, giving us Rnu plus X. And then they said give the mechanism. After giving the mechanism, right? Since from the mechanism you can tell that it is SN1. So how do you give the kinetics? You simply say, since it is SN1, right? It's going to be a first order what? Kinetics. Now, the moment they ask you for kinetics, you must give them this rate law. You must give them the what? So let's assume this guy was CH3, something like this. So for you to give them the kinetics, you say it is a first order kinetics. You must state it there, right? You now say my rate law is equal to K into, remember this Rx is a substrate, right? In this case, what's the substrate? This entire stuff here. You now say CH3, that is it. Do you understand what I just did here? So basically, you've given them the rate law. You've also told them it is SN1, right? First order kinetics. So that's one of the ways question can be asked. So let's do fast so that we can take questions and then answer. Please, this mechanism simply means show the process. What I did earlier. First step, formation of the carbocation. Second step, attack by the nucleophile on the carbocation. That's what you're supposed to show here. With the curly arrows, how the minus is moving to meet the plus, and how the plus is moving out by itself. You otago? This is another way that one can use to distinguish SN1 from SN2. Now let me explain something now. This stuff, they hardly ask this in exams, very, very rare, but just in case. Well, now what do we mean by part inversion? Now, when something is when something is actually being replaced, SN2, let me just use this. I think that's one of the major reasons why they always start with SN2. SN2 is basically inversion. It means that if this is the X, as this guy is going out, the nucleophile is coming from the back. So the nucleophile enters here. Initially, this was what it was. But after the nucleophile entered, it now becomes like this. That means for SN2, this guy is inversion. That means it's attaching at the back, opposite of the position where the living group was. Another example is, imagine somebody sitting down. You want to replace the person. The person is not going to stand up totally. Imagine the person adjusting, right? The person is going right. Maybe the person is going this way and you're coming from this way. That means you're coming from the opposite direction of that person. That is for SN2. But for SN1, SN1 is a case where before the nucleophile, listen, for SN2, the nucleophile enters as the living group is leaving, right? Both of them occur simultaneously. But in SN1, the nucleophile, the living group will leave totally, just like somebody standing up from the chair. A new person is about to sit down. There are two options. It's either I wait for that person to come out and may I enter, or as the person is standing up, me I'm sitting down without even waiting for the person. So if, for example, now we have two doors here, door 1 plus this, and we have door 1, and we have dot 2. And this is a substrate. This guy loses this X, and we have this, right? Since this guy is not inversion, it means that somebody can come from this dot 1 and sit down. Remember, initially, this was where the X was. So the person that is coming from this dot 1 is at the opposite side from this guy. This person should come and sit down. This guy is going to be what? Inversion. If another person comes from this particular dot 2, which this X is pointing towards, that guy is going to be what? That means you're retaining the same side that this guy is moving out from. Is it not so? But if you're coming from the opposite side, it's what? Inversion. So this retention is the most common one. Now, racemization, if you could remember in Chem 260, racemic mixture, when you mix R and S, right? So racemization is a case whereby you're mixing inversion and you're also mixing what? Retention. So get what? So anytime you see part inversion, part racemization, it means it is for what? Or anytime you see part inversion and part what? Retention, it is C for what? SN2 is fully what? Inversion. So this is where we're going to spend a lot of time. Please let me explain something here. When we talk about substrate for me, I feel, is the most important component of whether a reaction is going to follow SN1 or what? SN2. Please note this. The best substrate for SN1 is tertiary alkyl halide. Now, the reason why we call it tertiary is because the carbon bearing the halogen is attached to 1, 2, 3. Now, this is the best substrate for this. Substrate reactivity towards SN1. Substrate reactivity towards SN1. Class, there are some substrates that can never undergo SN1 reaction. We're going to see it shortly. So I said substrate reactivity towards SN1 is, the best one is tertiary alkyl. Tertiary alkyl is greater than secondary. Is greater than primary. Please, these two can never undergo SN1. Never. Now, this is the best. This is the best for SN1. This guy can actually try. This guy can also exhibit SN1, but it's not the best. But you see methyl, you see primary alkyl, and you see methyl, they can never. So the moment they give you a reaction, and the substrate is actually this, it's not going to undergo. So what they normally do most times is to give you secondary alkyl halide. Once they give you secondary alkyl halide, right, this particular one now can either go SN1 or it can go SN2. So now you have to now look further for evidence that will make it go to either SN1 or SN2. So that is it. In addition, allylic halide can also undergo SN1. Now, what's allylic? This guy can also undergo SN1. Why? Because if you remove this guy becomes positive charge. There is a conjugated system here, right? Anything that, now, why is this guy undergoing SN1? Because the carbocation that will be formed from tertiary is stable. Tertiary carbocation is very stable. Secondary is also very stable. So the reason why methyl cannot, this guy cannot undergo, because primary carbocation is very, very unstable. So every reaction proceeds or follows a direction that will make the intermediate form that will be stable. If passing through this particular direction will make me unstable, I will avoid it. So the reason why this is the best is because tertiary carbocation is very, very stable. Secondary is also stable, but you see, primary and methyl, they are very, very what? Unstable. That is why they cannot. Now, this guy, allylic halide, can undergo SN1 because this guy can be stable. In addition to this guy, we also have an benzylic halide. So this allylic halide can also exhibit SN1. Why? Because of resonance. If this guy goes out, the plus will be here. Now, yes, this guy is primary. This carbocation is primary because it's attached to just a single carbonation also. But because of this double bond, this guy can move here, and this plus comes here. So resonance makes this guy to be more stable. So this guy, same thing is applicable here. If this guy should go out here, here becomes plus, right? There's a resonance, plus single bond and double bond, is not so? So take note of this. So therefore, the possible halides or substrate that can undergo SN1 is tertiary is the best, allylic halide is also the best, benzylic halide is also what? Best. Secondary is not the best, but it can undergo. Primary can never undergo. Methyl can never undergo. So if you see a reaction that is given to you and they use primary alkyl halide, just forget about SN1. Look towards what? SN2. So these guys that cannot undergo SN1 are best for what? SN2. These ones that undergoes SN1 cannot undergo what? Apart from this guy, right? Best for SN1 cannot undergo SN2. This guy is not the best, he's just there. So this guy can undergo both SN1 and SN2. But this guy that cannot undergo SN1 is the best for what? SN2. So that's it. So we're going to take example briefly. I won't wait. Please put down. A living group is an atom or group of atoms that is displaced as a stable species. Is an atom or group of atoms that is displaced as a stable species, taking with it the bonding electron. Is an atom or group of atoms that is displaced as a stable species, taking with it its bonding electron. We have two types of living group. We have good living group, and we have good living group, and we have poor living group. Now, what is good living group? Let me explain something. Good living groups are those groups that are easily displaced by a nucleophile. They go out easily. A poor living group are those ones that they wouldn't want to go out. Like, if I refuse to go out, how will something else come in? So if I'm a good living group, it means that once I notice something is coming, I'll leave. So what describes a good living group? Please put down. Good living groups are groups that are easily displaced in a substitution reaction. They are groups that are easily displaced in a substitution reaction. Generally, they are stable anions or conjugate bases of strong acid. When something is a stable anion, it simply means that if it comes out as an ion, it will be very stable. living group, since they are coming out, you know, there are people that when you merge them with people, right, they'll be very stable. But the moment you tell them to stand on their own, they won't be very stable. So can this guy stand alone as an ion? Because it's going to come out as an anion, which is minus, right? If they are not stable, they cannot be a good living group. Oh, I know fully well that if I get detached from this guy, I'll be very, very unstable. I will not want to get detached. I'll hold on to it. But if I know very well that if I get detached, I'll be very stable. Of course, what's there? If she has to leave, I'll leave. Now, so how do we know stable anion? Very simple. The stable anions we have, the most common anions we normally encounter is always the halogens. Always the what? Halogens are the common living groups, right? Because they are always what? X. We have fluorine, bromine, and what? Now, the more as you go down the group, right, they become more stable. Fluorine is very, very unstable. Fluorine is very unstable. F minus can never stand, you can never see this guy stay on its own. That is why HF, as a matter of fact, is a weak acid. You know that HF is a weak acid? Because if you have H plus and F minus, this guy, since this guy is the most electronegative element in the periodic table, it will always attract this guy back to itself. It can never stand alone because it's very unstable, right? So as you go down the group, iodine minus is a stable anion. This guy can stand on its own, so it's a very good living group. Bromine, right? Chlorine can. So these three guys can be considered a good living group because they can stay on their own. HCl is considered a strong acid because this guy can stay as H plus and what? But you can never see this. This guy will always want to go back. So these three guys, 1, 2, 3, are stable like this on their own. But this guy is very, very unstable. Is it not so? So therefore, when we talk about stable anions, example of good living group, we have Cl minus, Br minus, and I minus. That is based on stable anions. If you don't want to use this definition now, use this. Conjugate base of what? Strong acid. Class. Between HF and HI, which of these is the strongest acid? Is HI. This guy is stronger than this. As a matter of fact, this is a weak acid. So since this guy is a strong acid, the conjugate base of this guy, conjugate base simply means the substance that will be formed when that guy loses hydrogen. So if this guy should lose hydrogen, what is going to be formed is what? So the conjugate base of HI is what? I minus. So this will act as a good living group. So anytime you see a substrate like this, you have to do something to this guy. OH is a poor living group. This OH, the three orga, like the overall chairman of poor living groups, F, OH, and what? This is a strong base. This is a base. FOC is a base. These three guys are poor living group. Why? Because they will hardly get detached. They always want to get attached to the R. So for you to remove them, you go force them to go out. There are people that stay in your house. You cannot tell them to go out in peace.
Okay, so we have the poor living group. So we said poor living groups are groups that are not easily substituted by a nucleophile. Right, they are strong bases, including less stable anions. So if we could recall, for good living group, we said good living group are weak bases, stable anions, and conjugate base of strong acids. All right, so for poor living groups, they are actually strong bases, less stable anion, and conjugate base of weak acids. All right, you can see fluoride ion, hydroxide, alkoxide, and amide ion.
Now, when we say solvent, solvent is actually an integral part of reaction because it's more like if you want to take a drug, you have to take water. That does not mean you cannot do it without the water, right? But the process, the smoothness of the drug taking will not be nice, right? So solvent is actually an integral part of reaction. Now, for substitution reaction, we have two types of solvents, polar protic and polar protic. Now, polar simply means something that has a positive and a what? That's what polar means. Now, when we say polar protic solvent, protic simply means the positive part of that is hydrogen. because this protic is gotten from proton. And proton is something, hydrogen that has a what? Positive. So polar protic solvents are solvents in which the positive part is hydrogen. Right? They are solvents in which the positive part is what? Hydrogen. The negative part can be what? Anything else. It means that proton, the positive part is hydrogen. Polar protic simply means the positive part can be any other thing apart from what? Hydrogen. Example of polar protic solvent is water. When water splits, we have H plus and what? OH minus. Another example is alcohol. Right? Alcohol has formula of this. When this guy splits, you have RO minus and what? H plus. So basically, polar protic solvents are solvents that the positive component is a hydrogen. Whereas polar protic, polar means they will be positive and they'll be negative. But the positive component will not be hydrogen. So example of this guy is acetone. Acetone is CH3, C double bond to O, CH3. So when you break this guy, this place becomes minus and here becomes what? Plus. So this is polar. If you could remember Chem 260, addition reaction of Chem 260, the double bond here will break into minus and what? Plus. Another example is acetonitrile. Now this is acetone, and we have acetonitrile, which is this guy, 1, 2, 3. If this bond should break, here becomes minus, here becomes plus. So there are a lot of them which I would like to give to us. So we have DMF, we have DMSO, we have H,
All right. Polar aprotic is best for SN2. Right. So they may ask you which of this is best for SN1 and SN2. So polar aprotic is best for SN2, whereas polar protic is best for SN1. Right. So this will be given to you guys in form of, they give you a reaction, they might just put the solvent on top of the arrows, and then you'll be expected to tell which of the mechanism the reaction is going to follow. So solvents can be used to tell if a reaction is going to follow SN1 or SN2. All right, looking at this reaction here, right, you can see A plus B. If you have DMF on top of that, now DMF is polar protic. That means this particular reaction here would go through the SN2 mechanism. But what if they decide to change that DMF to something else? As you can see, DMF is under polar protic. So what if I decide to change that DMF to water? So in this case now, water is a polar protic. So if I change the DMF to water, the reaction will no longer follow the SN2. But this time around, it's going to be following the SN1 mechanism. Now, there are cases where if water is given to you, right, that reaction is going to follow SN1 mechanism. So a case where water is acting as the solvent and also as the nucleophile, that process is called solvolysis. So if water is given to you, water is going to double both as a solvent and also as a...
Please put down. The rate of SN1 reaction is independent of the nature of the nucleophile. Since the rate determining step of SN1 reaction does not involve a nucleophile. And as such, whether the nucleophile is a strong or a weak nucleophile, it will not affect the rate of the reaction. A weaker nucleophile, in brackets, non-basic or less basic, is favored for substitution reaction, mostly SN1. Mostly SN1. Now, the reason why I said that is because substitution reaction is always in competition with elimination reaction. If you use a nucleophile that is a very strong base, that will no longer act as a nucleophile, because look at this. If I have something like this, X, and I have, let's say, this, this, and this. Please look up. And I have a base. I have a nucleophile. A base, a base is going for the hydrogen because base are substances that accept proton. Is it not so? They will go for the hydrogen and pull it out. They are not replacing it. They are doing what? Pulling it out. But a nucleophile, if this nucleophile is weaker nucleophile, that means it's not a strong base. The work of this guy is just to replace the what? The X. So if the nucleophile is a very strong base, substitution reaction will be suppressed against what? Elimination reaction. Because if this guy should attack the hydrogen, that's not substitution. That's elimination reaction because you're removing something, you're not replacing it. Right? So if the nucleophile, for a substitution reaction to take place, that guy has to be a weak base or non-basic at all. Right? He has to be what? A weak base or what? Non-basic. Because if it's so now, if you're asked in exams, maybe after they gave you a question, they say I, give the mechanism II, give the kinetics IV, give the energy diagram, or show the energy diagram. Now, this place is basically the substrate. Imagine I have something like, let's say they gave me something like this, CH3, CBr plus NaOH, giving me CH3 plus. So this is what I'm going to do. This place now will now be CH3. The nucleophile here is just the OH. All right, so here it becomes, this is the first, remember SN1 reaction is a two-step process. The first step is to form a carbocation. The second step is to form the product. So here will now be the carbocation, which is CH3, C plus this X, in this case now, is Br. So we now come to this guy, this becomes CH3. Now, but when I wrote these exams, I'll show you what I did. What I did was that I used Rx. I used this stuff. Then on the side of my paper, I labeled this. And I said Rx is equals to CH3 C Br, because I didn't have enough time. And I'll say my Nu is this. My R plus. You understand what I just did here? So I just, because if I'm to do it here, it will make my drawing not look fine. And of course, and nobody's going to mark me wrong, because if you look at Rx, I labeled it here, you see the same thing. So you can choose to write it directly. You can choose to also write this and then label each of them. So rank the following compounds in order of SN1 reactivity. Start with the most reactive. First thing first, we have these three guys. This is I and this is II. So we're going to rank this guy first. Okay. I know fully well that for SN1, the order of reactivity is tertiary alkyl is greater than what? Secondary is greater than what? It's greater than what? Methyl. So how will I know it's tertiary? I'll come to the carbon that is bearing the bromine, the halogen. Look at this. All right. So here now, if I detach this guy from here, here becomes a positive charge, right? Now, let's check the type of carbocation that we have here. This guy is attached to 1, 2, and what? 3. This is what? Tertiary. Let's look at this guy. This point is where the carbon is attached to. You can still leave this guy here. This guy is attached to 1 and 2. This is what? Secondary. Let's look at this guy. This guy is attached to 1 and what? 2. So between these three guys, this guy is the most reactive because it's a tertiary alkyl. Good. So I'm going to label this guy so that it will be very easy for us to, So let's call this guy A. Let's call this guy B. And let's call this guy C so that we don't have to rewrite this compound. Now, like I said, for SN1 reactivity, tertiary is the most reactive. After tertiary is secondary, you know so. So based on this, this is tertiary because the carbon bearing the bromine, which is this guy, is attached to 1, 2, and 3. So this is tertiary. Now this guy is secondary. The carbon bearing this halogen is attached to 1 and 2, secondary. This guy is also secondary. Now, between these two secondary, that is where we want to exercise more muscle. Now, between this guy and this guy, this will be more stable than this. Why? Because this guy has more alkyl groups. Alkyl groups are plus I. Positive inductive effect means that they will keep releasing electrons, right? And let's say the reason why tertiary is more stable than primary, than secondary, is because of plus I. If something is positive, the charge is localized. If I have something that releases electron to this guy, it will neutralize or stabilizes this, right? So the reason why this guy is positive and is stable is because the electrons here are used to neutralize or stabilize this guy. So between the B and the C, please look at this. So this is the most stable, right? This is secondary, this is secondary. So we are trying to see which of these two secondary is more stable. If you notice, this guy have 3 alk 1, 2, 3. This guy has how many? 2. So the more alkyl group we have, right, the more stable the carbocation would be. So this will be more stable than this. Because this guy, they are secondary, but this carbon has 1, 2, 3 alkyl, but this carbon has just 1, 2, right? So this will be more stable than this. So this becomes A is more stable than what? C. And C is more stable than what? B. So that is the answer for that guy. Now for this guy, yes, past question, 2019. This is 2019 past question. Now between these three guys, which of them in order of reactivity? This guy can now. Which of the following pair is more nucleophilic? Give reasons for your choice in each case. And it's important for us to know that more basic substances are more nucleophilic. Stronger base are stronger nucleophiles. Point number 1. Good afternoon. Strong base are better nucleophiles. Number 1. Point number 2. Negatively charged nucleophiles are more nucleophilic than neutral or positively charged. The next point is nucleophilicity increases down the group in the periodic table. That means for group 6, oxygen, sulfur, selenium, sulfur is more nucleophilic than oxygen. Selenium is not nucleophilic than this guy. So these are the 3 points I would like us to note before we jump into this question. All right, class, look. The question says, which of the following pairs is more nucleophilic? Hello. Give reason for your choice in each case. Now, between these two guys, which of them is more nucleophilic, class? Because this guy is what? Is sharp. Sharp nucleophiles are more nucleophilic than neutral. Now, this is this is the answer. This guy is more nucleophilic than this guy. Now, between this and this, which of them is more nucleophilic? Because if you notice, every other thing here remains the same. Just the ends. And nucleophilicity increases as you go down the wall.
All right, for the next question, which says explain the reasons which of this reaction below is faster. We're going to be treating this when we are done with SN2 explanation. So for now, we'll skip this.
So there are 2 mechanisms for substitution nucleophilic. The mechanisms are the SN1 and the what? So yesterday we discussed extensively on SN1. So today we want to actually do the same for SN2. Now we have characteristics here. Now these characteristics, what are the importance? If we actually explain all of this, they give you a question and then you're asked to give the mechanism. Now this serves as the evidence and also features of SN2. Like the mechanism for SN2 is different from that of SN1. The kinetics of SN2 is different from that of SN1. Stereochemistry, substrates, and all of them. If you understand this guy fully very well, like what they said here, I've taken down the question. They might give you a question and they say, give the mechanism of this reaction. Now, they will not tell you that it is SN1. They will not tell you that it is SN2. All you just need to do is look at the question very well. Which terminology in that question can be likened to SN2? For example, now, they say a reaction proceeds via a one-step mechanism, right? A one-step mechanism is that for what? SN2. Anyway, so without wasting so much time, so let's look at the first one. Reaction mechanism. SN2 reaction occurs in a single step. Therefore, it is a one-step process. The reaction is concerted. The reaction is concerted. Please, let's put it down as a point. So you can just put it as the first asterisk. Right? Now, once you've written the first one, it's a one-step process, full stop. The reaction is concerted. That should be a continuation, right? Before we move down to point 2. Now, concerted simply means two things are taking place at a time: the breaking of the old bonds and the formation of the what? New bonds. So please put down. Concerted means that the breaking of the old bonds and formation of the new bonds occurs at the same time. Occurs at the same time. Let's look at the next point. The reaction is generally described as a backside attack of the nucleophile. This is because the nucleophile approaches the carbon bearing the leaving group from the back at position 180 degrees. Look at this. Let's say, for example, now we have the nucleophile is always coming from the back. We have the nucleophile here, and then we have plus, let's say, Rx. Now, this is basically going to go like this, and this comes like this. Now, this nucleophile is always going to come from the back, not just from the back. Anyhow, if the substrate is written like this, the back of this guy is this. Like, it's always at an angle of 180 degrees. So if this is a bond holding this guy, count 180 degrees from here. That is where the nucleophile is going to come from. So one of the characteristics of this guy is that it proceeds via a backside attack. Now, having said that, now this is what is going to happen. In the case of SN1, it was a two-step process. The first step was formation of the carbocation, isn't it so? But in this case now, it's a one-step process. And one-step process will always give rise to transition states. Give rise to what? Or which in most cases we call it intermediate. So this becomes this guy. Now, please, I'm going to give us another reaction. I'm just trying to explain something here. Now, this is more like saying that as this guy is pulling out, this guy is being attached. Is it not so? Are you listening? Now, this is not a full bond. If you put a full bond here, you're wrong. You should actually follow up with a dotted line. It means that as this guy is shifting out, right, this nucleophile is getting attached to this guy. As simple as that. So the next thing we're going to have here is plus X. So this is basically what we mean by stereochemical inversion. The leaving group was initially on the right-hand side, right? Now the nucleophile is now coming, is attaching at the what? Left. But you can only use the word stereochemical inversion if the carbon is a chiral carbon. If the carbon is a what? That means if the carbon here was initially R, right? Now, opposite of R is what? S. So that's basically what we mean. This may not make sense to us. So I would like to, put down the next guy. We have this. Let's assume this stuff is like this. CH3. Because the best substrate for SN2 reaction is methyl halide. So let's use the best substrate. I'll tell us the reason why this guy is the best substrate for that. Remember, the nucleophile is coming from the back, right? So the back don't have to be crowded. If the back is crowded, it's not going to allow this guy to proceed in a 180 degrees, right? So that's why this guy is always preferring substrate that is less crowded. So here, this line If you don't do this line, I don't know what you're doing. That's not mechanism. Of course, you'll not get your full mark. So this becomes the carbon. I have 3 hydrogen pointed out this way. This is 3, 1, 2, 3. We have this. Huh? All right, so this becomes this at TS, transition state. Now this is the easiest, this is the most simple mechanism to write. So from here, please listen up. You can only put the nucleophile on the left if the carbon is chiral. If the carbon is what? Now, is this carbon chiral? What is a chiral carbon? Carbon that has 4 different substances, right? You can see that 3 types of substituent which is hydrogen is attached. So this guy is not chiral. So the N can retain the front position. But normally, if the carbon is chiral, the N will not retain the front position. It has to come to what? Back. Because if you put it at the back or front, it doesn't really matter when this guy is not chiral. So you come here, my product becomes CH3 Nu plus X minus. So this is a mechanism of SN2 reaction. The nucleophile, just like I said, will always approach the carbon bearing the leaving group from the back at an angle of 180 degrees. Right? So all of this stuff is something that they can make as a statement in the question, and then from the statement you can actually picture it. Oh, this guy is SN2. It's a reaction proceeds via a backside attack, right? According to the equation below. Give the mechanism of the reaction. Obviously, the moment they say backside attack is SN2. So that is it. All right, so the reaction and mechanism is done. So that's why I said formation of a new bond is formed at the same time with formation of an old bond, or breaking of old one and formation of a new one. Because this guy, as this guy is breaking out, the X is breaking out, this guy is forming. That's why we call it concerted. 2 things. Can you name? Now, before we look at the next guy, please look up. If you could remember yesterday when I was talking about kinetics, I said that this first SN1 reaction is a first order kinetics, right? Because the first step is a rate determining step. In the case of SN2, SN2 is a second order kinetics, right? That means both the nucleophile and the substrate are involved in forming the transition state. This is transition state, right? The faster this guy is formed, the faster the product. If this guy is not formed, this guy will not be formed, right? Because every chemical reaction has an intermediate, right? It's more like you're climbing a hill. That's why we have the energy diagram. This transition state is this top, and from here is the energy of activation from normal chemistry. The energy required, minimum amount of energy required to get to this point. So if this guy gets here to this point, to come down here is always very simple. So since the nucleophile and the substrates are actually needed to form the transition state, it therefore means that 2 substances will be required to determine the chemical kinetics. And that's why we call this guy what? SN2. Substitution nucleophilic bimolecular. Because 2 substances are needed for the to determine the rate of the reaction. In SN1, substitution nucleophilic unimolecular, only 1 substance was needed to determine the rate or how fast. Is it not so? So the reason why we call this guy SN2 is because 2 molecules, the nucleophile and the substrate, is needed to determine the what? Kinetics. All right. So let's quickly look at the kinetics. Please put down. SN2 reaction is a second order kinetics. The rate of SN2 reaction is dependent on both the nucleophile and the substrate. The rate of SN2 reaction is dependent on both the nucleophile and the substrate. The rate of SN2 reaction is dependent on both the nucleophile and the substrate. That is, the rate law for SN2 reaction will be rate equals to K substrate and nucleophile. That is it. Rate equals to K. This K is rate constant. and this is a substrate, and this is a nucleophile. All right. So if I'm to use this guy, if I'm to use this particular reaction, now let's assume this was a reaction they gave to us. At this nucleophile, let's assume this nucleophile were to be OH minus. Let's assume this guy were to be OH minus. It means that this guy, this place now, is going to be, and this guy will be what? So if I want to replicate, like imagine they gave me this reaction and they said, give the mechanism of this reaction. Let's say CH3, please just give me 1 minute. X plus NaOH, giving us CH3OH plus Na. They give you something like this in exam. This is how it works. This is how they will always give it to you. They give you a reaction and you're asked to give the mechanism. This is one of the ways. The second way is they will just give you the reactant and they will not give you the what? Products. So give the product and give the mechanism. Right? So how will I know that this guy is going to follow SN1 and we're going to look at that shortly. Now, since we are talking about SN2, this reaction is fully under SN2, you know, so because the substrate here, right, this is methyl substrate and it's best for SN2. Now, they say give the mechanism of this reaction. I, give the kinetics. Give the what? The mechanism of this reaction you have here is what we have here. So this guy, OH minus is what is going to act as a nucleophile. You know, so this guy, when you want to rewrite the mechanism, you need to take the OH to the left hand side, which is a nucleophile. Because for SN2, it's a must. You can never put OH in front. If you put OH in front, you fail it. But one of the characteristics of SN2 is that it's a what? Backside. That is not for fancy, right? So if you come and put OH, for SN1, you can put it anywhere. But for SN2, it's a must. This is what differentiates SN2. It must come from the back. So this guy comes here. This is a mechanism of this reaction. So this reaction we have here, this is a mechanism. I need to see the curly arrows. I need to see my transition what? State. All right. So I've given them the mechanism and they say I should give the kinetics of this reaction. I'll say, for this same reaction now, I'll come here. I'll say kinetics, the reaction is a second order what? Kinetics. And remember, rate law, you must write your rate law. Rate law, I'm not going to come and say rate law, I'll just write it at once. Rate law is K into what? Substrate and what? In exams, I don't even have to write this. What is a substrate? Replace it. What is a nucleophile? So this becomes rate is equals to, the substrate is CH3, what? X. And what's a nucleophile? That is the kinetics of this reaction. SN2 reaction occurs with inversion of stereochemistry. This is only possible if the carbon bearing the leaving group is a chiral carbon. This is only possible if the carbon bearing the leaving group is a chiral carbon. Please look up. Everybody should look up. First thing first, this is one of the most difficult parts to do because here there is no product. You have to give the product and then give the mechanism. Now, looking at this guy, this alkyl halide. This CN is a nucleophile here. This acetone is a solvent. Remember I told us yesterday that acetone is a polar protic. So polar protic is best for SN2. It's best for what? So the product of this reaction would be if you don't want to stress yourself, opposite of this is dash and this is wedge. Opposite of dash is what? Wedge. So doing this means that this is actually entering opposite. So this is a product of this guy, NaBr. First thing, this is a product. So this is SN2 substitution reaction. This Cn substituted Br, right? Now let's look at the mechanism of this guy. That's right or well. Now this is I'm just giving you the product of this. This in your scene, the opposite of this is this. Remember, this is a chiral carbon, right? So it means that this is going to proceed with inversion of stereochemistry. So this thing, just watch. Since we've actually decided, or we've concluded that it's SN2, because of this solvent, acetone is for SN2, polar aprotic. It's not so. SN2 means that the nucleophile will always come from the back. This was what they gave me. So you say Na is always plus, Cn is always what? Minus and plus. Which of this is a nucleophile? Minus. So I can come here and say Cn alone, right? Plus this guy breaks out, this bond breaks, and the minus is placed on this. It's not so. Now this guy comes here. Okay, no, this guy has no, he cannot indicate whether it's SN1 or SN2 because it's just a nucleophile. No, it's asking whether can we, remember I said we don't usually use nucleophile to determine whether a reaction is going to be SN1 or SN2. Yeah, so nucleophile has no big, so but solvent has a big influence. All right, so here, please, for those guys, you can still put the Na plus, but this stuff should, this arrow should emanate from the minus. So now, the next thing we are going for is the transition state. Can you guys, come on, allow me now? You got it, you got it. Please, this line, there is always 1, 2, 3, 1, 2, 3, Br. Now look at this. This is equivalent to what with that same compound. This CH3, this is CH3, right? I can say this is my transition state. Is it not so? Now, you can now come here and put all right, if you want to do it that way, they see and you can just decide, okay, if I don't want to write it this way, class, this is what I'm going to do. You can simply say, look at how this stuff is. This is starting from down. I can decide to start from up. So this can be this, this, this. Cn will now be up. Here, Br was down. Here, I will now change this guy. Cn will now be up. But just use this simple pattern I just told us now. Once they give you dash in your product, just use wedge. To avoid stress, just put wedge. Use the same pattern. Put anybody that sees wedge, this is opposite of what? This finish. Okay, so please hope you have this stuff inside your notes. So what if you don't want to use a skeletal structure? This becomes Na plus. They'll mark you correctly. Yes. They'll still mark you correct. But me, I always prefer if they give you words, give them dash to avoid issues. I've given you guys 2 examples now. And you guys disappointed me. I'm so.
Yes.
So this is meant to be Cn, not OH. Alright. Written here on the board. So I said for substrate. Substrate is basically what is reacting with those nucleophiles. All those stuff I was drawing that has dash, all of this. I'm going to be explaining shortly. Now I said methyl halide and primary alkyl halides are the best substrate for SN2 reaction. Now, secondary alkyl halide can also undergo SN2. However, tertiary alkyl will not undergo SN2. Now, so substrate reactivity in order of SN2, substrate reactivity, because they might give you list of substrate and they say arrange the following in order of reactivity towards SN2. substrate reactivity towards SN2. So let's do this. The one that reacts the most is methyl halide, which is something like this. This is methyl, and this is halide. Is greater than primary alkyl. I'll tell us why it's called primary alkyl halide. Is greater than secondary. Is greater than now this methyl halide. Now this is primary alkyl, this is secondary, and this is tertiary. Now, why do we call this guy methyl halide? As the name implies, this is methyl and this is halide. This is not a primary alkyl. Now, primary alkyl, by definition, is basically an alkyl where the carbon bearing the halogen is attached to just one carbon. That's for primary. So this carbon, which is CH2, is the one holding this X. Is it not so? Now, this guy is further attached to just one carbon. That's why it's primary. Now, in the case of secondary, this carbon is the one bearing the X or holding the X. This guy is further attached to two carbons, this and this, right? Now, in this case now, this is tertiary alkyl. This guy bearing the X is attached to 1, 2, and what? Now, why do we say that these two are the best for SN2? Now, this guy never is because SN2 is a backside attack. Remember, the nucleophile comes from the what? So the back needs to be less crowded. If the back is crowded, it's not going to allow the nucleophile to meet this guy, therefore inhibiting the reaction to take place, right? So the less crowded the backside is, the better the nucleophile attacking this guy. So in this case now, this guy doesn't really have much substituents attached to this. So the nucleophile can just easily from the back and meet this guy. This guy, same thing. But secondary has a bit crowdiness, but not as much as what? Tertiary. So in case you are being asked, why is it that tertiary alkyl halide cannot undergo SN2 reaction? Yes, the word crowd, but in chemistry, we cannot use the word crowd. Please, in chemistry, if you're being asked, state the reason why tertiary alkyl halide is the worst substrate for SN2. Because of what we call what? Which type of effect do we call that? Steric effect. Steric. Please, steric effect is the effect that results from space. Stereo, space. So, the reason why tertiary alkyl halide cannot undergo SN2 is because of steric effects, right? Because here, there is more crowding at the back. Here, there is what? Less crowd. So, in exams, you will not come and say crowding and not crowding. SN2 is best for methyl halide is best for SN2 because of less steric effects found here. This guy is worse because of high steric effects. So steric effect is high in tertiary alkyl because this guy has more crowded substituent, whereas this guy has less steric effect. So that's the answer. So definitely I have a question here which I would like to solve it at once before we proceed to. I'm not going to solve this. I'll do this, and this. Now imagine they give us something like this. Methyl bromide plus sodium hydroxide giving us methanol and sodium bromide. And the question is, give the mechanism of this reaction. There's nothing here to tell us, no solvent, nothing. Can you tell which type of reaction is this, SN1 or SN2? Please, this is SN2. In as much as there is no solvent here, now you look at the substrate. Which type of substrate is this? Methyl halide. This guy is less crowded, right? And methyl halide is best for which type of substitution? So that is it. So like once they give you a reaction, the conditions given to you or the substrate is going to give you an idea of whether it's going to be SN1 or what? SN2. All right. You guys would have allowed that guy to express himself. All right, so let's look at solvents. I did living group yesterday, so it's the same thing. This is for solvents. We have two types of solvents. So let's say we have polar protic, we have polar aprotic. Now the likes of acetone. Now this is best for SN2. Acetone, DMF, dimethyl formamide. We have DM, we have HMPT. So this guy, I'm going to explain. This guy is water, alcohol, and carboxylic acid. Now this is best for SN1. Now why do we say so? Now let me explain something. When they say something is polar, polar means something that has a dipole. Dipole simply means two poles. One is positive and one is what? So when they say something is polar, it simply means that there is a plus and there's a what? A minus. So when they say polar protic, protic is gotten from the word proton. And proton simply means hydrogen ion. So when they say protic, listen. When they say polar protic simply means this solvent has a positive end and a negative end. But the positive end is proton, which is going to be what? H plus. That's what it means. Polar protic means polar is something that has positive and what? Negative. When they now say polar protic, it means that the positive component is having what? Hydrogen. That's what it means, because protic is gotten from proton, and proton is what? H plus. So if you look at this guy, if water should dissociate, water is O minus and what? The positive component of this guy is with the hydrogen. If alcohol should dissociate, RO minus and what? H plus. If carboxylic acid should dissociate, COO minus and what? H plus. So this is basically what it means. But you see these other guys, this simply means that acetone, acetonitrile, DMF, DMSO, HMPT, these are all solvents. The positive component is not on hydrogen, it's on carbon. It's a what? It's on what? Carbon. That's what it means. And don't worry, just start continuing. So that so when they say polar aprotic means we have positive and negative, but the positive is not hydrogen, is on carbon. Let me give us an example of aprotic. Now, acetone is what we all know as propanone in Chem 260. Now, CH3, C double bonded to O, and CH3. This is formula for acetone. Now, when this guy breaks, here becomes minus and here becomes plus. So this compound has a positive and it has a what? But the positive is not on hydrogen. If it is on hydrogen, it will be what? If it's not on hydrogen, it will be what? So that's it. Which one? This one. Yes, both of them. This one takes minus, this one takes plus. So take note of polar aprotic are best for what? Polar aprotic are best for what? Please put down. Nucleophiles are chemical species that donate an electron pair to form a chemical bond. More reactive nucleophiles are more basic. If we're in class yesterday, I think I gave us this stuff already, so you might decide not to write. In brackets, nucleophilicity increases with basicity. Now, this is an example. Now, this is it. These are bases. right? This is a base, this is a base, this is a base, this is a base. All of them, they all have negative charge, so they can act as a nucleophile. Anything that can donate electrons is basically considered as a nucleophile. But do not forget that a base also possesses a negative charge, right? So for something to be a very strong nucleophile, it has to be a very strong base. So this is one of the reasons. More reactive nucleophiles are more basic. This base is stronger than this guy, and this guy is stronger than this, and this guy is stronger than this. That means in terms of nucleophile, this is the strongest amongst the four of them, right? So imagine they give you this, but I doubt, because there is no basis that they will give us something like this. They don't expect you to be cramming all bases in your head, right? But now look at the next point, point number 2. Negative charge nucleophiles are usually more nucleophilic than neutral nucleophiles. Negatively charged nucleophiles are usually more nucleophilic than neutral nucleophiles. Negatively charged nucleophiles are usually more nucleophilic than neutral nucleophiles. Now, we have an example, O minus. Now, this particular one now is something they can ask you guys because there's a pattern. The last but not the least. Nucleophilicity increases as we go down the group of the periodic table because of increase in size and polarizability. I'll give you an example. That is why if I have OHO, let me give you this example. In group 6, oxygen, sulfur, selenium, right? If I have this, let's say between 3 of them, 1, 2, 3. If they give me 3 species that have every other thing is constant apart from O, S, and what? Example, I had H here. Here becomes H. I had another one here. If you notice, H is constant amongst 3 of them. What is changing is just this, this, and this. And if you notice, 3 of them belong to the same group. Oxygen, sulfur, and selenium belongs to group 6. So as you're going down the group, this guy is becoming more nucleophilic than the other. So imagine they say HS minus and OH minus, which is more nucleophilic. This. Why? Because nucleophilicity increases what? Sulfur is down the group compared to what? Oxygen. So here, I would say HSE is more nucleophilic, greater than HS minus, greater than what? HO. So that is that for the nucleophile. And then, what was the last guy? Energy diagram, right? So let's look at the energy diagram, class. Both SN1 has energy diagram, SN2 also have. So most times in exams, they can ask you to give the mechanism, give the kinetics, give the stereochemistry, and give the energy diagram. Each of those guys have what distinguishes them from the other. So the energy diagram for SN2 is just like the normal energy diagram you know for reactions. This is going to be, now this is Rx plus nucleophile. This is R nucleophile plus X. And this guy, please, like I said, most times you may not really have enough space to draw the transition state here. You can just indicate TS and then come by the side and write your TS. Now, what do I mean exactly? All those reactions we have been doing. Those reactions we have been doing, those things that I always enclose in a square bracket, right? Because of this class, I think we did two or three examples and we enclosed stuff in bracket, right? Those stuff that is always enclosed in a bracket at the middle of the reaction is a transition word. So if you're asked to give the energy, please, okay, let's just do example. I don't like talking plenty. So there is this guy is potential. This is the energy. You don't have to put the potential, just put the energy. And this is the progress of the reaction. Progress of reaction. So I'm going to write a mechanism by the side. So let's see how we can interpret this mechanism using the energy diagram. Now this is the nature of the question, right? They mean you guys so well. This is the nature of how the question could come. You're asked to give the mechanism of such reaction. Afterwards, give us the kinetics, and afterwards, give us the energy diagram. So I'll start by saying, first, which type of reaction is this? Is it substitution reaction? Before you start talking about the mechanism, you need to understand whether it is substitution or elimination reaction. So initially, we had Br attached to this CH3, and on the product side, we now have Cn. So there's been a replacement of one functional group. or a substitution. So this substitution reaction. Now, substitution reaction, we have SN1 and what? So is this guy SN1 or is SN2? The first is because of the substrate. The second is because of the what? Solvent. So the mechanism, so I'll say solution. The mechanism will now be I. Now, since it's SN2 reaction is characterized by a backside what? Attack. So this becomes my nucleophile is going to be Cn plus H3 Br. This guy breaks out from here. This guy breaks out from here. So we'll have this to be Cn now this is the transition state. Now the product becomes CH3 Cn. Then we have your NABR. So this is TS. When I gave us that energy diagram, right? The apex point I indicated it with TS, right? So I'm going to represent this particular reaction with the energy diagram. So that's why I gave us this. Remember they said give the mechanism, which is what we just did here. Now number 2 is that give the kinetics. So I'll say since it is SN2, the kinetics is a second order kinetics. Kinetics is a what? Second order kinetics. You have to give the rate law. So therefore, the rate law, anytime you're asked for the kinetics, you must always give the rate law. So the rate law is equal to K. The substrate is CH3 what? Br. And what is the nucleophile? Cn. Since it's a second order kinetics, it is dependent on both this guy and this guy. Right? So now let's look at the energy diagram. I. So I'll say I, energy diagram. So I'll come here. I'll put this. The energy diagram will move from here. Here. Now the left hand side is a reactant. What is the reactant on this reaction? CH3 Br plus Cn. Now here, I'll say what? Transition state. So that anytime, once I say TS, remember in this reaction, I had earlier said that the TS is what this guy is. So when I come here and I say TS, somebody can equally say, oh, this guy is referring to what? This. So this is what I was supposed to draw here. Right? But because of lack of space, I'm just going to draw this guy and then indicate it here. So my product will now be CH3 Cn plus what? Br minus. So that's I've answered the mechanism, which is this guy. I've answered the kinetics, which is this, and I've answered the energy diagram, which is this.
Now, this question is basically asking us to tell which of them will react faster under SN2 mechanism. So currently now, I'm solving the first one. So the first one is going to follow the SN1 because the solvent is polar protic, which is water, whereas the second reaction would follow SN2. So just watch out and see how we explain this.
Water is a polar. Water is a polar protic solvent that favors the SN1. So because of this, we're going to follow the SN1 mechanism. So what is the mechanism for this reaction? The mechanism here, first step, mechanism for SN1, formation of carbocation, which is safe as loss of the leading group, formation of the carbocation. So we have this. If you can decide not to put this like this, you can just remove it. and put your BR. Just as in your product, change the change the substrate. So this goes up. First step is formation of carbocation, which is loss of the leading group. When this go up, you have a slope. Now, the second step is when water is used as a nucleophile, the way water adds is different from the way other reagents are. Water does not really add as OH and H. Water adds as water as a whole, and then the H will not go on break out. So this is what we have. So we have this. What I usually have is one pen. So this guy is what is going to come in. I repeat, water does not act like other substance. NaOH to others. NaOH is actually, listen, the reason why we normally add this guy, we normally write it as Na plus and what? Because this is ionic in nature. It is what? Ionic. But water is not ionic in nature. So you cannot break it as plus and minus just yet. You're going to add it that way, and then at the end of the day, you pull out your hydrogen. So it's not the same thing like this is ionic, and we know that ionic is always positive and minus always coming together. So here, the water is going to add as a whole. So I'm going to maintain that. Look at what I'm about to do now, in case you're going to be confused. Remember that SN2 reaction proceeds. Okay, this is SN1. Oh, thank God. I'll put this like this. Please don't write it before you write, just look up. This is this. But this is the same thing as saying what? Is it the same thing? Instead of saying H2, instead of saying normally if you add the water, this is supposed to be H2O or like this. Right? But it's best you don't put it like this. So the best way to write it is you put OH on one side because this is what you want to be left here. You now drag what? H. So this is the one that is going to be. Alright? So from here now, you can now say this now becomes I'm not comfortable putting this guy, you can put it down. No flex. See? Please, if you feel comfortable putting it down, no problem because SN1 proceed their retention and see what? Inversion. There's no problem. So first thing, we eliminate the PR and form the carbocation here. The next guy, the water, remember, water does not break as H plus and OH. As a matter of fact, that reminds the solvent. Is it recording? Acetone is a solvent for SN2. Just in case you might be wondering what acetone is, this is acetone. So for the fact that acetone is a rapid reaction is SN2. So let's see how we're going to split that young man. Anybody carry for come and tell you. It seems I'm not buying gas and taking this lab. And what? Please look up. Let's solve this guy. Now, The nucleophile, since this guy is an ionic compound, you can split it. In the case of a covalent compound, you don't have to split it, just add it like that and pull out the hydrogen. This guy is ionic because metal is combining with a non-metal. So you put down the, can choose to say Na plus, Cl minus. Now this is actually the nucleophile. Now you come here, you have, I can decide to do this stuff class. It's still the same thing like what I have there. Please, you have to stop saying use the normal one. If you use the normal one, that means you keep cramming. What if this happens? All I'm just doing here, I've not done something different. I'm only trying to position this guy so that it can get a nice transition state. That's all I'm trying to do. It's still the same thing. So this guy attack this guy, and this guy does what? Blinks. Now this becomes, now you have CN class of. How many of us are still confused? This we done it. You okay, Bob? Yes. Once again, once you've gotten this, always put this. One is always going to point, or two do what? Now look at this point. There's CH3 there, and there's CH3 there. That means one of the substrates on this guy is CH3 and what? CH2. This guy is another one, CH what? 3. You know that the CH here, the H be up. So we have H, CH3, CH2, CH3. So this becomes what did I just do there? Can say or alternatively sodium bromide. When you want to get the inverse of this, please look up. You want to get the inverse of this, try to start from here. Don't just turn this guy. Let's just turn this together. This guy, this place was down, right? Opposite of down is what? Up. So this is up. This guy was up. Opposite of up is what? Down. So this becomes this, and this. So this is now our what? Here. Because if you swap that guy, opposite of this, here was down, is now up. Here was up, is now what? Down. Here was down, is now what? Here was up, is now what? Down. That is the inverse. So this nucleophile is now going to be what? CL. So which of these two do you prefer, the first or the second?